Okay, so this is in continuation of my tutorial classes. So today we will discuss the problems based on the increasing and decreasing functions, as well as that some Maclaurin series expansion or Taylor series expansion. So this is the tutorial 11. So let's take one example first. So that the function f so that the function f defined age f x equal to x cube minus 6x square plus 12x minus 4 when x belongs to the real number is an increasing function in every interval of real line, whatever may be the interval is real. So let us see the solution. Here we will make use of the Lagrange's mean value theorem. What the Lagrange's mean value theorem says, that if the function Lagrange's mean value theorem says that suppose a function f is a continuous function over the closed interval say a b, differentiable on an open interval a b, then there exists a point c in the interval such that f b minus f a over b minus a is the derivative of the function at a point c, where the c lies between a and b. Now, if I take the 2 point x 2 and x 1 in the interval a b, say a b, where x 1 is less than x 2, and over the interval x 1 x 2, if we apply the mean value theorem, then we get f of x 2 minus f of x 1 divided by x 2 minus x 1 is nothing but the derivative of the function at certain point x I, where the x I lies between x 1 and x 2. Now, from here it implies that the f x 2 minus f x 1 is equal to x 2 minus x 1 into f prime x I. Now, if our f prime x I is positive, then x 2 is already greater than x 1. So, right hand side is positive. Therefore, f is an increasing function. F x 2 is greater than f x 1 when x 1 is less than x 2. So, f is increasing, f is an increasing function. So, this is the Lagrange's mean value theorem. We will use this result to establish that this function is an increasing function. So, what we have to do is we have to differentiate the function f with respect to x and see the behavior of f dash x over the any arbitrary interval of R, whether it is positive, strictly positive, or strictly negative, or maybe the oscillating. So, if we look the function f dash and differentiate the derivative will come out to 3 x square minus 12 x plus 12, and that is the same as 3 x square minus 4 x plus 3 plus 4, that is equal to x minus 2 whole square into 3. Now, whatever the x may be, x is in any arbitrary interval a b of R, this quantity will always be positive. Therefore, the derivative of the function is positive. Hence, by Lagrange's mean value theorem, we can say that the function f x is an increasing function over any interval a b of R, and that completes the proof because of this discussion which we have made it. Okay. So, this second question is also in these similar lines, but different, slightly different. Okay. The question second says find the limit of this, find limit of x tends to 0 1 plus x to the power 1 by x minus e divided by x. Now, this result, if you look, it based on the L'Hospital's rule. Why? Because when x is 0, limiting value of 1 plus 1, limit of 1 plus x raised to the power 1 by x when x tends to 0 is always be e. This is a standard result. So, when you take the limiting value or when you take the limit or upper numerator and denominator separately, it will take the form 0 by 0, and 0 by 0 is an indeterminate form. So, we cannot say the value is 0 or value is 1 or like it depends on the behavior of the function when x tends to 0. So, in order to solve such a problem, we use the L'Hospital's rule. Again, the L'Hospital's rule is a consequence of our Lagrange's mean value theorem. We are not going, we have discussed this in the theory part. What L'Hospital's rule says that in order to find the limit of the function f x by g x when x tends to say a, we differentiate the numerator and denominator separately and take the limit when x tends to a. So, if this is of the form 0 by 0, then in order to find the limiting value of this ratio, we differentiate the numerator with respect to x, denominator with respect to a individually separately, and then substitute x equal to a. Now, if this limit exists, if the right hand side limit exists, then we say the left hand limit will exist and basically and equal to the value limit of limit of f prime x over g prime x when x tends to a. So, this is known as the last pressure. So, here it is of the 0 by 0 form. Hence, to find the limit of this, apply the L'Hospital's rule and differentiate numerator and denominator separately. So, this is the same as d over dx 1 plus x raised to the power 1 by x minus of course minus e divided by derivative of this x and then take the limit as x tends to 0. To find the derivative of this, we get let y is equal to 1 plus x raised to the power 1 by x. So, take the log y becomes log of 1 plus x by x and then differentiate it with respect to x. So, when you differentiate with respect to x, this is 1 by y dy by dx, this is denominator into derivative of the numerator minus numerator into derivative of the denominator divided by x square. So, basically dy by dx becomes by means 1 plus x to the power 1 by x, and then this will be equal to x minus 1 plus x log 1 plus x divided by x square 1 plus x. So, this is the dividend. So, this limit is suppose L, then we get L is equal to limit x tends to 0 1 plus x raised to the power 1 by x into x minus 1 plus x log of 1 plus x and divide by x square 1 plus x. Now, limit of this is e. So, we can simply write down this thing h limit 1 plus 1 plus x raised to the power 1 by x as x tends to 0 into limit as x tends to 0 x minus 1 plus x log 1 plus x divided by x square 1 plus x. Now, the limit of this is e, and this limit is of the form 0 by 0, x tends to 0. So, it is 0 by 0. So, again apply the L'Hospital's rule. So, L'Hospital's rule says differentiate the numerator and denominator separately. So, we get 1 minus 1 plus x divided by 1 plus x minus log of 1 plus x, and this is equal to x square. So, x square means 2 x plus x cube 3 x square. This is okay. So, differentiate this and then take the limit as x tends to 0. So, this will get cancelled and we get from here is e minus this is minus first function derivative for second function derivative of this and then this is. So, here we are getting minus outside limit x tends to 0 log of 1 plus x 2 x 3 x square, where again when you substitute x equal to 0 is again the indeterminate case. So, again apply the L'Hospital's rule, and when you get the L'Hospital's rule you are getting e, differentiate this 1 plus x 2 plus 6 x limit x tends to 0, and that is the answer is minus e by 2. So, answer will be that is minus e by 2. Okay. So, that will be equal to answer. Clear? So, we can repeatedly we can apply the L'Hospital's rule to get the limiting behavior of this. Now, same example another example based on this, again L'Hospital's rule, evaluate limit x tends to 0 1 by x minus cot x. Now, this is of the form infinity minus infinity. So, again it is an indeterminate form. So, in order to solve it we have to apply the L'Hospital's rule, but when you apply the L'Hospital's rule there is no numerator denominator. So, we will try to put it in the form of 0 over 0, and this can be written as cot means cos by sin. So, we can say sin x minus x cos x divided by x sin x, and limit x tends to 0. So, let this limit is L like this. Now, it is 0 over 0 form. Apply the L'Hospital's rule. So, when you apply the L'Hospital's rule, the value differentiate the numerator and denominator separately, and we get from here is L is equal to limit x tends to 0. The derivative of sin x is cos x minus cosine x minus x into cos is sin x with minus sign divided by first function sin x derivative x and then plus x cosine x. So, when you take the value x tends to 0, it is basically 0 by 0 again. So, further apply this result, we get L'Hospital's rule, and we get first is x cosine x plus sin x divided by cosine x plus x sin x with minus sign and then plus cosine x. So, again x tends to 0, this part is 0, this is 0, this is 1. So, 1 plus 1 2 and 0. So, basically the limiting value of this when x tends to 0 is 0. So, that is what is get L becomes 0. So, that is the answer for this question. exercise 4. Say evaluate this limit x tends to 0 sin x by x raised to the power 1 by x. Now, we know the limit of this x tends to 0 sin x by x is 1. So, basically this is of the form 1 to the power infinity. Again it is an indeterminate form. So, in order to prove find the value of this, we have to use the L'Hospital rule and then bring it either in the form of 0 by 0 or infinity by infinity. Now, this can be done as follows. Let y is sin x by x to the power 1 by x. Then what will be the log of y? Log of y will be log of sin x divided by x divided by x, and this is log of x 1 by x into log. Now, if we take the limit of this as y tends to 0 log of y, this is the same as limit x tends to 0 limit x tends to 0 is the same as limit log of limit x tends to 0 of this term. Is it not? Log of y means log of this part. So, limit of this part sin x by x, or you can say limit of log sin x by x divided by x, this one. Now, when x tends to 0, sin x by x is 1. So, numerator is 0, denominator is also 0. So, it is basically 0 over 0 form. Therefore, to apply the L'Hospital rule, again use the so to find the limit, apply the L'Hospital rule, and the L'Hospital rule says differentiate numerator and denominator separately and then substitute x equal to 0. So, we get limit x tends to 0 1 by x log sin x by x, and this is 0 by 0. So, by L'Hospital rule, this is equal to log में 1 upon this. So, x over sin x into x cosine x over this, okay, and then derivative of x will be 1. So, limit of this x tends to 0. Okay. Now, this will be the same as limit of this x tends to x by sin x when x tends to 0 into limit of this x tends to 0 x cosine x minus sin x divided by x square. Now, this limit is 1. So, we are not bothering about it. The second limit is limit x tends to 0 x cosine x minus sin x by x square, again it is 0 by 0. So, apply again L'Hospital rule, and when you use the L'Hospital rule, differentiate numerator and denominator. So, x of sin x with minus sin plus cosine x minus cosine x divided by 2x. So, again this is of the form limit x tends to 0 minus sin x by 2 sin x by 2, and that will be equal to 0. So, this is the what? This limit is the limit of x tends to 0 log of y. Therefore, the y is equal to e to the power 0 1. That will be the answer for it. Okay. So, this clear. So, these are few examples based on the L'Hospital rule and increasing decreasing function. Now, let us see the some examples where Taylor series and Maclaurin series can. So, find the Maclaurin series series expansion of the function log 3 plus 4x about the point x equal to 0. We know the Maclaurin series expansion, if the function f x is continuous, then differentiable, defined in the neighborhood of the 0, then one can expand this function f x as f 0 f prime 0 over factorial 1 plus f double prime 0 over factorial 2 x square f prime 0 into x, okay, x, and like this. So, last term will be f n 0 y factorial n x to the power n. So, and so on. So, this will go there, and up to here when you truncate, this is called the remainder terms and there. So, this is, so basically the function f x is here log of 3 plus 4 x. So, f of 0 becomes log 3. What is the f prime 0 x? F prime x becomes 3 plus 4 x and then multiply by 4. So, f prime 0 becomes 4 by 3, and then f double dash x is minus 3 plus 4 x whole square and then 4 x whole, so 4 square. So, f double prime 0 becomes minus 4 square by 3 square and continue. So, if we see the behavior of the term, we can write f n x in a similar way. We can write minus 1 to the power n plus 1, minus 1 to the power n plus 1, 4 to the power n into factorial n minus 1 into 3 plus 4 n 4 x, 3 plus 4 x power minus n, n is 1 to 3. So, when you substitute n is equal to 1, the derivative this f prime is coming to be 4 over 3 plus 4 x, n is equal to 2, this value coming and continue. So, what will be the f n 0? The f n 0, that is the nth derivative. So, this will come out to be minus 1 to the power n plus 1, 4 to the power n and then 3, when you take 3 outside. So, 3 4 by 3 to the power n into factorial n minus 1, and then substitute. Therefore, the Maclaurin expansion of this 3 plus 4 x will be is nothing but the sigma n is 0 to infinity f n 0 over factorial n into x to the power n. Substitute it, we get this one. Okay. So, we get from here is log 3 plus sigma n is 1 to infinity minus 1 to the power n plus 1, 4 by 3 to the power n divide by n into x to the power n. Well, after simplification, we will get this. So, this is the Maclaurin series expansion of this function. Then see the one problem based on this, find the Taylor series expansion of the function f x equal to 7 by of the function f x equal to 7 over x to the power 4 about x equal to minus 3. So, we have this result f x is there, we can write is x minus h by h like this. So, we can expand this function around the power of x, and this expansion will be equal to f of x minus 1 or so on, or we can say x naught. This we can also write x naught plus x naught minus s. So, we can say x minus x naught. So, in the power of x minus x naught, we can say f x naught plus x minus x naught f prime x naught plus x minus x naught whole square by factorial to f double dash x naught and continue. So, this is the Taylor series expansion of the function, and the last term will say nth term will be factorial n f n x naught and so on. So, here our x naught is 3, x naught is minus 3, and x minus x naught is equal to x plus 3. So, when you expand it in the form of this, we are getting the derivative f of x is 7 x 4. So, f of minus 3, this is coming to be f of minus 3. So, 7 over 3 to the power 4, then f prime x is coming to be minus 7 into 4 x to the power minus 5, f double dash x is coming to be 7 4 5 x to the power minus 6 and so on. And so, nth derivative of this will be minus 1 to the power n 7 4 5 6 up to n plus 3 into x to the power minus n plus 4, and that from here we can get the term and get the function f x equal to f x plus 3 minus 3, and that will be equal to n equal to 0 to infinity f of minus 3 by factorial 3 factorial n f factorial n, and then x plus 3 f n x plus 3 power n. So, find the value and substitute. So, that will be the answer. Thank you very much. This one.